Okay, I hope that y'all can hear me. I have a tendency to talk pretty loudly when I'm presenting, so on the boards back there, definitely provide some attenuation if necessary. Good morning. My name is Eric Johnson. I'm a regional engineering manager with Lucent Technologies. I'm based out of Portland. It was a very exciting gray drive down for me today. I was quite surprised to see that the weather turned so rapidly. Yesterday was an absolutely gorgeous day, and I did see blue peeking through this morning, but c'est la vie. I was contacted very late last week by E.J. von Schomburg, who is one of our liaisons into the 802.11 committee, and unfortunately he was not able to make the show as much as he had wanted to. So he indirectly asked me to come in and to present to you. What I'd like to talk about today is essentially the state of wireless, and I'm going to be focusing on 802.11 and some of its derivatives. This is intended to be an overview, and I'll need to get some feedback from you in a second as to what kind of expertise we have in the audience. But it is not intended to be an exhaustive rundown on all wireless technologies. I'll touch on wireless loop, for instance. I won't be touching on wireless sonnet or some of the other high cap systems. On a scale of 1 to, let's say, 1 to 5, could I get a show of hands as to who fits in, with 1 being lowest and 5 being highest level of expertise? How many of you fall into the 1 to 2 category? Okay, how about the 3 to 4 category? And how about 5? Okay, so it looks about 3 to 4 is about probably where we're at. What I'm going to do is I'm going to give you some information which may be rehashed for some of you. And if it turns out that it's not what you want to hear, let's make this interactive. Just give me the hand sign, and I'll go ahead and start moving forward. In addition to talking about some of the different, at least the current state of 802.11, I also want to, at the end of this discussion, to give you some indication of what some of the organizations that I've dealt with, or at least that my staff has dealt with, what kind of applications are using wireless in. And also I'd like to talk a little bit about what, at least from my perspective, is happening out at Bell Labs. And we've got some very interesting things developing in that area. The point I wanted to make with this slide is that there are some very real reasons why 802.11 is in the current state that it's in, and much of these are driven by people such as yourselves who have made requests for certain levels of technology. What we're now seeing is a maturation of 802.11 as far as local area networks are concerned, and now we're starting to see some development of the technology into the WAN. And when you start moving into the WAN, there's going to be certain limitations in terms of how 802.11 operates. As a consequence, we're now starting to see an evolution of that technology into something that's more suited for wide area network use, particularly, let's say, for instance, for kind of a quasi-local loop system. And that technology today is fairly proprietary. There are a number of vendors out there, Lucent, BreezeCom, Aeronet, that are developing these technologies. I want to expect within a year or two that you'll start to see some standardization effort wrap up in respect to how those technologies are working. Most importantly, I think for many of the customers that I've seen, cost control is a primary consideration as to why wireless is deployed. If you look at the cost of developing infrastructure, wire infrastructure, can be very, very expensive. Let's say $500 to $1,000 per drop for wire applications. And many of the applications that I've seen have been derived as a result of that cost. They're looking for a significant way of reducing the cost. Additionally, there are areas where flexibility, extreme flexibility, is the case. We've got one customer who is looking at deploying wireless LAN technologies on high-speed trains, and for telemetry and other information coming from these trains as they move by. So that's something that just simply can't be handled by some of the traditional networking technologies. Where we're at now, my talk is decidedly nonpartisan. However, because of the nature of what I do, I want to point out, I'm not trying to hide anything from you here, I want to point out that Publan in this case is a product set that's made by Lucent. I'm not going to be talking about Publan as a product, but more as a technology. This is going to be some wide area network wireless technology. We've seen a number of older and slower technologies deployed. CD-PD received a lot of press in the last, probably 3 to 4 years ago. And we also have seen a great number of different mechanisms surrounding the deployment of wireless local loop. And that continues today. However, because of the advances that we've seen with 802.11 moving from 1 and 2 megabits per second of sustained transmission throughput, and now with the draft 10 of the 802.11 spec having been ratified, I believe, in the last couple of days, and someone please keep me honest on this, the vote was in May. Now we see transmission rates sustained between 2 and approximately 11 megabits per second. And that's where this technology comes in. And of key importance here is to notice that this particular technology is portable. It doesn't require a fixed set of stations per se. You can deploy this technology on as I alluded to earlier, trucks. You can deploy it in much the same way as it's being deployed here with some of the wireless workstations here. You can roam. You can move about. And again, the same cannot necessarily be said for some of these technologies. CD-PD, of course, was a hallmark in that area for portability. Unfortunately, in terms of speed, it was fairly limited. And of course, when you look at the economics too, with some of the wireless technologies, cost can be very, very low, but then you get extreme throughput. In this case, 11 megabits per second. So, makes for a very compelling argument for deploying this technology. Here's some comparisons of the technology. I know this is a bit difficult to read, but if you can look at the presentation. By the way, if you've not downloaded the presentation, you can get it at ftp.mindsprings.com/users/esjohnson. Name of the file is nanog99.zip. And what we're looking at for the 802.11 and other variants are the following characteristics: high speed and portable, typically mobile end devices. And right now we're operating in the 2.4 gigahertz realm, which I'll talk to in just a second. By the way, there's variability in the performance between 2 megabits and 11 megabits per second. There are a number of different scenarios in which you would see lower performance, well, one being distance or noise. And ideally, you'll look at something toward 11 megabits per second. I'm not aware of anyone running at that speed, typically in about the 5 to 8 megabit per second realm max. This is license-free spectrum, and currently we're looking at a spectrum window of about 84 megahertz in the 2.4 gig realm. Now, in future versions of the standard, there is a great deal of talk right now and work toward a 5.8 gigahertz standard. And, of course, the spectrum in that's going to be much wider. We're looking at about 125 megahertz. This is going to be great. This is really going to open up a number of other interesting applications. The 802.11 standard is currently based on direct sequence technology, where you over a certain spectrum, you take advantage of the full spectrum full frequency spectrum. There are some technologies that are based on frequency hopping. They are generally proprietary in nature. And interestingly enough, despite the fact that 802.11 uses direct sequencing, some of the emerging technologies are now falling back to frequency hopping. Frequency hopping has a unique capability in closed environments of selecting the best frequency to use, and also has some inherent, I'll call it noise rejection capabilities. Direct sequence is typically works best in wide open spaces. And I believe that was one of the compelling reasons to go with direct sequence technology. Now this is an interesting slide. This is, in some respects, this is based on some of my team's experience with these different technologies. When you look at some of the older 802.11 technologies, we typically saw transmission range with a standard low gain antenna in the 1 megabit to 2 megabit range, and you could really extend some of these trials out. We did a trial out at the city of the Dalles in eastern Oregon, and the buildings that they had within the city were built well over 100 years ago and have these very, very thick, 3.5 foot thick sandstone walls, and based on red iron in the ceiling and based on the radios and the type of antenna we were using, we were actually able to, with between 1 and 2 meg, get up to about 300 to 400 feet away from a single access point, single central node. Now, in some of the other experiments we've done out in southern Colorado, we've actually seen, using that same standard low gain antenna, we've actually seen dramatic increases in the amount of in the distance between nodes and transmission rates. Now, typically what will happen is if you're operating at a higher speed, let's say 2 megabits per second, as you start to move away, as the signal-to-noise ratio degrades, then you'll see the system start to ratchet back to a lower speed until ultimately, to conserve or to preserve the integrity of the data, it'll simply drop off. It's kind of a cliff roll-off. Now, theoretically, 802.11 is offering up to 11 megabits per second, as I had mentioned before. To date, I've not seen any systems being able to perform up at that level, typically between the 5 and the 8 megabit per second sustained rate. Not all applications require this level of performance. Some applications will work well down at the 1 megabit level. Again, the draft 10 of the standard has been ratified or will very, very soon be ratified. The vote was in May. Unfortunately, I was not able to get the specific date of the vote. We're looking at one common MAC for 802.11. The interesting thing about this is if you look at the standard, the PHY description is in some respects independent of radio frequency technology. In other words, it is conceivable that you could use something like infrared and still maintain the kind of connectivity and performance that you're looking for. I'm not aware of anyone operating in an infrared mode or even doing any development for that matter. But the nice thing about the standard is it allows you to swap out PHY sets if necessary. And of course, 5.2 gigahertz is not here yet. There's a lot of development effort taking place in that realm. I would expect within the next 12 to 24 months to see a great deal of that technology starting to be deployed. A lot of that has to do with FCC regulations too, and opening up that particular spectrum. 802.11, it was formed as a result of a large consortium of industry participation, and it was optimized specifically for land use. However, you're starting to see some deployment of this technology into the WAN, and I'm going to talk here in just a few minutes as to how you do that. The core technology itself remains unaltered, or I don't want to say unaltered, but the core technology remains the same in terms of transceivers, but you start to find extended application with the varying types of antenna that you can apply. There must be at least 20 different types of antenna I've seen applied to this technology. I'm going to skip over this for right now. So here are some of the typical configurations that you'll see. First and foremost is a standard wireless LAN. This really doesn't even have, this is really not scalable. It's something like you would use in this room. You'd have a single access point, or actually no access point. You'd have all workstations contributing as part of a base LAN infrastructure. Very simplistic, not too scalable. Then you can then start applying a wire and actually developing a small wire-based network, but still employ some wireless stations within this network. I don't see too much of this, but this is where we start to see some of the applications. This is where you'll actually have a wired net, and then you'll have one or perhaps more what I'm calling access points. These are, for instance, in this show, I believe it was mentioned we've got 11 access points throughout the hotel. What this allows you to do is to essentially set up some nice frequency or some nice coverage path, regardless of where you are in the hotel. You walk around and you'll connect up to a point. This is typically where a great deal of businesses, commercial businesses, are operating. Now, if we look at the next slide where we have multiple, what we start to see is a very large-scale deployment. A number of universities that we're working with are typically deploying this technology, and doing so using a variety of different antenna types. Within the campus itself, you'll see a great number of people connecting up to any particular access point, and as they roam through the campus, then they'll simply connect through another cell. It's very, very scalable. Some of the universities that we are working with, we've seen in excess of 6,000 people in attach mode. Of course, another variant of this is when you use it essentially in riser applications, performing exactly the same function. Now, this is where it gets interesting. This is where you take the inherent LAN-oriented technology, and by use of, for instance, something like a Yagi or a parabolic antenna of some kind, then you can get some point-to-point service. Now, in this case, we've had a couple of universities who have driven from between 5 up to 30 miles using this technology, and it depends on the type of antenna that you're using. If you're using a moderate gain antenna like a Yagi, which might be between 12 and let's say 16 dB a gain, then you can typically go up to let's say 5 or 6 miles. I did have one instance where I believe it was University of Colorado, where they needed to, University of Denver, where they needed to go an extreme distance, upwards of 30 miles, and by using a 24 dB gain parabolic, we were able to see about 30 miles of transmission. And this is really interesting too, because if you use those parabolics in a much closer range, you can tend to provide some problems for some users. Those parabolics are very hot, and you put a chicken in front of that thing, it'll cook it, despite the low output. And of course, then what we can do is we can take some directional, low gain or moderate gain directional antennas such as Yagi, and then we can essentially point those back line of sight back to an omnidirectional antenna at a central site. This is where I think you're going to see most of the application. This is where ISPs come into play. This is where you're serving a large campus. You'll have a single Yagi that's attached to your customer site or to the campus site, and then you simply go back to your service provider. This is not a product. I'm not running into product or marketing here. Let me point out the different components here. These are typical of any manufacturer. We've got a very low gain internal antenna here. Typically, you find cards in the form of a PCMCIA adapter with a built-in antenna, very low gain antenna, and then you'll find access points, which is essentially a wall-mounted or a red iron-mounted device to which all of the PCs or other devices attach to. And then you see also ISA carriers now, where you can this module where you can take this technology and plug it into an ISA carrier. Now, I said I was going to deviate slightly from 802.11, and this is where the deviation comes in. We're now seeing the development and deployment of technologies for wireless loop that essentially provides you with serial services. In this case, technology such as this, where you're using Yagis or omnidirectional antennas, can emulate T1 or E1 and provides you with a variety of different outputs. This is decidedly not 802.11 right now. This is proprietary technology. Fact of the matter is that it's coming out very quickly, and you're going to see a great number of service providers using it because it allows you to define the bandwidth that you want to use for a particular application. This is an example of a Yagi antenna. Yagis are around, about this big, typically fairly lightweight, mass-mounted, and again, you're going to see about a 14 dB gain at 2.4 gigahertz. The complement to the Yagi is an omnidirectional antenna. This is typically about 7 dB gain. It looks like a light, we call them lightsabers. They're about this tall, and not due to the movie. And it's a fairly simple mass-mounted unit. Combine the Yagi and the omnidirectional antenna together, and it forms a basis for a nice wide area LAN. And again, all depending on line of sight, weather, et cetera, you can find some great utility between these two different types of technologies. Now, this is an interesting thing too. We've been doing some development with an organization where they are mounting this technology, which is a omnidirectional vehicle antenna, about 6 to 8 inches tall, on the top of trucks. So when trucks pull into various truck stops or what have you, the trucks will automatically register with the LAN and then be up and running. Very interesting technology. It's low gain, 8 dB, but it's a ruggedized and obviously weatherproof device. So again, much of the utility that you're going to find is based on your antenna design, not necessarily on the technology. I had to use some product information here, but again, this is typical of industry. These are the different types of distances that you can realize with speed and throughput being up here on the top, and then gain, antenna and gain over here. So obviously with a 24 dB gain antenna, one of these big parabolic chicken cookers, you can see upwards of 30 miles. I'm going to skip past this. Okay, 802.11 evolution. We see a great number of people who are interested in voice over IP right now, and this makes a very nice natural migration into that sort of technology. Also, again, ISPs are very focused on this type of technology, especially the non-802.11, the proprietary technologies, where you can essentially structure a great number of connections back to, in a hierarchical format, back to a service provider, and essentially use use it in essence as an adjunct to a local loop. Also, you're going to see development. We're currently at 11 megabits per second at 802.11. You're going to eventually see deployment of 30 megabits per second as they really crank this technology up. Now, I've got 2 minutes left. I'm going to talk a little bit about futures. I don't know if any of you read the Wired 2 or 3 months ago, the Wired article about BLAST. But I want to give you some perspective into what Bell Labs is doing. I'm sure that there are out here a number of people who remember PEP. If you're old telebit hacks, PEP was a data link protocol used by telebit modems. And essentially, what it did is it took the entire usable frequency of the telephone line, 2,700 hertz, and broke it up into a number of smaller subcarriers and channels. And the effective baud rate, if you will, of PEP was something on the order of 5 to 7 baud. However, by applying symbolized information over that broad spectrum of frequencies, it was able to realize throughput of about 19.2K. And BLAST is essentially the same thing. Now, BLAST is interesting, except that it allows you to, the potential exists for a very, very high degree of throughput, many tens of megabits per second. It's very high efficiency. We're looking at about 40 bits per second per hertz at normal SNRs. And then if you expand it across a great number of frequencies, you can start to see where this technology may go. This is purely experimental, purely in the lab. I've got a white paper here. If anyone is interested in digging in, this will really get your propeller spinning. Additionally, one of the interesting things about BLAST is that it exploits multipath versus avoids multipath. Okay, well, the great bane of wireless is one of the great banes of wireless is multipath, where you have signals bouncing off of buildings and such. It's especially prevalent within cities. something like BLAST, which will what BLAST does is, unlike conventional transmission and receiver structures where it's very serial, you have data coming in, goes out through a single antenna, typically over a single frequency, and then into a corresponding receiver unit, and then out as data. What something like BLAST will do is it will take that information, it'll encode it in a way that where it can be presented to multiple frequencies over multiple transmitters over an antenna array, and then the information will be sent out. It's symbolized information. When it gets to the other side, regardless of what path it took, the strongest signals will be picked up, will be decoded, and then the information is reassembled and put back at her. So it actually exploits multipath. This is very exciting stuff, and without getting marketing oriented on you, I believe at least that it has it has some great potential in the future. Whether or not it becomes a commercial product, I don't know, but it's certainly something that is happening within the wireless space right now. Finally, I wanted to leave you with some information regarding some further reading. If you're not, if you are not tuned into Bell Labs, you have the ability to get updates on on a great number of white papers that they develop and publish in the interest of forwarding science. If you go to this website, this will get you to the Bell Labs Technical Journal area, and they've got some very deep, I guess, for lack of a better description, publications on the state of wireless and essentially what's coming 2 to perhaps 5 years down the road. BLAST was one of the things that was featured in Bell Labs Technical Journal. It is free of charge, so I mean, go for it. There is a special wireless issue which might be of interest to you, and it's not out yet, but the July through September issue, Volume 4, Number 3, will be coming out here shortly, and you can download it in PDFs. Again, it's free of charge. And that is it. That is record time. I usually go for about 4 hours in a stretch. I don't think I have any time for questions at this point, but I will stick around if anyone would like to hit me up. Thank you very much. Thanks. Okay, great.
Question. Come on, Craig. I'll go to the mic. I was thinking maybe we have John go, and then we have questions in general, or is it really, Bill, is it wireless specific? Yeah. Okay. Well, no, we've got 2 wireless talks this morning.
I'll be happy to, yes. Yeah.
Okay, well, no, we can answer the questions now. It looks like Stephen is...
Did you want me to address the questions now? Or?
Looks like I see Stephen.
Okay. 2 questions really quickly. One from Stephen.
Wait, can't hear you.
Okay, so...
Wait, you have to introduce yourself first.
I'm Bill Woodcock, and that's Stephen Stewart.
Okay.
Hi there.
So you're talking about a future in which more and more things are point to multi-point, and I agree entirely. It looks to me like where things are going. And so we've done a lot of shopping around, and I've only found one product that seemed to have a good layer 2 forwarding table scheme built into it, and that would seem to me to be the only really sensible way of solving hidden transmitter problems. Can you discuss that a little bit, if there are other things that are happening, or if everybody does that and they just don't talk about it, or what the deal there is?
Yeah, I heard part of the question. Yeah, it might be better down here. If I understand the question correctly, you're asking about essentially bridging capabilities, but not necessarily at a, let's say, an Ethernet data link layer. Is that correct?
Right.
You're looking at essentially establishing a hierarchical network and then and bridging between those nodes. Absolutely. Again, I'm decidedly non-commercial in this. I'm non-partisan, but something like this access point will allow you to do that, where you can actually create a relay network of nodes. This particular device, and there are a number of other industry products like this, will accept 2 cards. One can be a card for local area, and then which is essentially I'll call it a point to multi-point. That is, this will be a central site going out to a number of different users, and then the second card can establish a network of these devices. Now that's entirely bridged. It's layer 2. There's also some proprietary technology that's coming out. And again, BreezeCom and Lucent and a number of other companies are deploying this, which is not 802.11 right now. And it allows you to create a hierarchical network specifically designed for WAN applications, where you can have, let's say, up to 600 separate nodes consolidating up into, let's say, 10 remote site nodes, and then ultimately back into the central carrier space.
So you're saying that box bridges, but its number of logical peers is limited by its number of physical interfaces?
No. Well, this particular technology in and of itself, if you're using a wireless relay network, is going to be limited. It is limited by the number of interfaces that you have. You'll have one of the cards that are serving a local area. The second card will be essentially a point-to-multipoint network, which allows you to network these devices together. But you're using one frequency. You're using one limited spectrum. So while it will work, it's not necessarily the best way to do it. Probably the best way to do it is to have these things wired back into a switch or some other more capable device, and let them simply serve the wireless application.
Yeah,
but yes, you can do that.
I mean, there are products out there right now that build a forwarding table and choose next hop based on signal strength.
Yes.
Which is the right way to do it.
Yes, absolutely.
But so the question is there a standard for that, or is there more than one vendor doing that?
There is more than one vendor doing that. Is there a standard for that? To be honest with you, I don't know. I can certainly take your name down, and what I can do is go back to some of the folks that, well, I've got the 802.11 standard on my PC, so I can look into there. I can also go and better yet, I can consult some of the people that do that on a daily basis and get an answer for you.
So I'm Stephen Stewart. My apologies to Craig, but I have to tell a short tale of woe before I ask my question, and additional apologies for the fact that it's operational in nature. I ran 915 megahertz in my house, and the distance between me and where I wanted to be wireless was about 30 feet, and life was good. And then I had a baby, and she's very nice, but the baby monitor would go click, 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 click every time I pressed a key at 915 megahertz, which was amusing until I started getting mail, and a megabyte of data going click, 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 click. Made my wife very angry. So I switched to 2.4 gigahertz, and life was good, until we started using the microwave oven. And when I use the microwave, all traffic stops.
Sure.
When I move to 5.2 gigahertz, how will I be screwed this time?
That's a good question, and while I can't specifically address or, for that matter, predict what's going to happen, based on the information I've seen, when you get up to in the 5 gig range, it's my understanding that there's going to be some immunity to that. Now, again, I would be happy to dig farther into that and talk to some of the people who really know, and get some information for you. But it's my understanding that there is going to be some rejection of
my microwave and my baby monitor.
Exactly. Now, how that affects all 2.4 gig products, I think it's going to be on a vendor by vendor basis. Certainly, I would expect that, given the fact that much of this technology is based on a well-defined and very mature standard, that they would all operate the same way. But now that goes.
Great. Well, thank you.
Okay. Thanks.
Okay.